Okay, so welcome back to Unit 5. Second part of this trend that we need to look at are the periodic trends. And there's really three things that you need to learn. You need to learn the trend for atomic size, okay, where are they bigger, where are they smaller? The trend for electronegativity, ooh, that's a fancy word we'll talk about in a minute. And then the trend for ionization energy. Now, I know these are fancy words and that's probably freaking you out a little bit, but trust me, it's fine. Atomic size is nice and simple. Once you understand that one, these two go hand in hand. Once you learn one, you've already learned the other without realizing it. So we're going to start with atomic size. When we're talking about the trend for atomic size, it's important to realize what we're actually talking about. It is nearly impossible to actually measure an atom. Not because they're so tiny, but because think about it. I got a nucleus, and then there's this thing around the nucleus, which if you remember is called the electron cloud. So the problem here is, let's say I've got a lovely little ruler. How in the world can you measure from one side of a cloud to another? That's not really going to happen, okay? There's no definite edge. You can't tell exactly what's going on there. Plus, everything is always in motion. It's constantly shifting. It's just not really an option. So what scientists did instead, since they couldn't focus on these guys, all right, this wasn't going to work, is they looked at diatomic atoms. Diatomics, if you remember, are, here's nucleus of one, here's nucleus of the other. It's two of the same atom that are joined together. So the scientist's idea was if I measure from nucleus to nucleus, all right, because these are solid structures, I can actually know where they are, and I cut that measurement in half, then that is going to tell me the radius. Now, is it perfect? No. Is it exact? No. But it's about as good as we're going to get. So the reality is we're not actually talking about the size of the atom. That's not actually what we measured. We really measured the atomic radius by looking at half the distance between these nuclei. So the big thing that you have to remember to understand any of this is by far the number one thing to remember, is in any atom, the nucleus has a positive charge. Remember, that nucleus is full of protons, which are positive, and neutrons, which have no charge. That means that overall has a positive charge. Around the nucleus are electrons. Now, we know we've got different levels. You know, there's my level 1, there's my level 2, there can be level 3. But these electrons have a negative charge. So what's going on here is we have an attraction between the positive nucleus and the negative electrons. That nucleus pulls the electrons toward it and keeps them from just like, whee, flying off into space. That pull also determines the size. Think about it. If I pull these electrons really close to me, that makes a much smaller atom. Okay, because if they're all really, really close, that thing is going to be tiny. If, on the other hand, I can't pull them very close, and they're like way far away, that's going to be a much bigger atom. So that's the basis of what we're talking about. So we're focusing on two things. We're going to focus on the periodic trend. Periodic trend means what happens as I go across the periodic table from left to right. Then we'll talk about the group trend, which is top to bottom. So as you go across the period, you add protons. Okay, so any row on the periodic table that you look at, you go from 11 to 12 to 13 to 14. You're adding protons. If you're adding protons, you are getting a stronger nucleus. So if you think about this, stronger nucleus means I have more of the ability to take those electrons and really pull them in closer. So as I go across, I'm actually going to have a smaller and smaller atom because that stronger nucleus, can really pull these guys in close. Okay? The outermost electrons in a single row are on the same level. So, if you look at this periodic table, if you go across a row, you'll see, for example, sodium, magnesium, aluminum, silicon, etc. All of these have their outermost electron on level 3. So just like this last drawing you were looking at, okay, we're not adding any extra levels. Now this one happens to just have one little circle. Humor me for a second. But they all have their electrons the farther the farthest away as everybody else. They're the same kind of level, all right? So this would be like 1 and 2 and then 3, and then 1 and 2 and then 3, and then 1 and 2. So we don't have to worry about that part when we're talking about going across a row on the periodic table. So when you look at the trend is very simply, as you go from left to right, the radius gets smaller. You're going to have your bigger atoms over here, and then as you go across this periodic table, they're going to get smaller and smaller and smaller. And that's essentially true for all of these rows. And obviously you know that the D and the F block we're ignoring because they don't follow patterns. With the group trend, when you go top to bottom, you're adding energy levels. So think about that for a second. If I am adding energy levels, there's my nucleus. Okay, if this guy has 2 levels, that automatically puts the electrons a certain distance away. But if I add a third one, that thing is logically getting bigger. Plus, a bigger issue here, a more important issue, is it's harder for the attraction to happen when you're this far away compared to when you're this far away. Think about magnets. You put them, a couple centimeters apart, they'll jump together. You put them 4 feet apart, nothing is going to happen. The other issue is something called shielding. So in addition to the distance being different, another problem here is there's other electrons right in here. Those electrons are kind of blocking the attraction between the valence and the nucleus. Here, there's even more electrons blocking. The example I used in class is it's kind of like trying to give somebody a hug with 2 people standing in between you. It's not a very good hug. And the more people you put between you and them, the worse your hug is going to be. So, if we look at the periodic table, if we have this guy and we look at it again, as we go from top to bottom down any row, we will be adding energy levels, having our shielding increase, and we're going to get bigger. So we'll have little, and then bigger, and then bigger, and then bigger, and then bigger. And again, we're ignoring this, and we're ignoring this. One more note that I want to put out there on shielding. Shielding is only an issue when we're looking top to bottom. We don't worry about shielding going across the periods because, like I said before, going across the period, everybody has the same energy levels. So all of them in a row will look like that, okay? Or all of them will look like that. Shielding is only an issue when you're adding energy levels, when you're going from top to bottom down the periodic table. The other 2 words that we talked about, okay, and then I'll show you kind of how to put all this together, are ionization energy and electronegativity. Ionization energy is the energy it takes to remove an electron, okay, to take an electron and pluck it off of a neutral atom. The first electron you do, that's the first ionization energy. Second electron's the second ionization energy, third is the third, etc., etc. And the reason this would happen is to increase stability. You think about sodium. Sodium has an electron configuration just like neons, but then it's got that 3s1. So if I can get rid of that 3s1 and pull it off, sodium is more stable. But I can't just lose it. Someone has to pull it off. So what ionization energy is that energy to pull off the electron. Okay, the example I used in class, Doritos. I actually held up that wonderful bag of Doritos and said ionization energy is how hard you have to work to get it away from me. That's literally what we're talking about. And there is a variance of it on the periodic table. So let's start with the group. As you go down a group, you got to remember the valence electrons are farther away. Okay, plus they're farther away and there's more shielding. You put those 2 things together, okay, it's going to be a lot easier for you to take off that electron. Okay, so this is going down a group. All right, so if you're more visual, I got one for you. Okay, here's me. Here's the bag of Doritos. If I'm holding it like that, it's going to take you, okay, a little bit of energy to get it away from me. But if I've got that Dorito bag and I'm like hugging it to me and I'm not letting go and I'm just holding on to that sucker for dear life, you ain't going to get it away. Electrons are no different, okay? If you're looking at the top of that periodic table, that small little atom has all of its electrons really tight to the nucleus. So it's going to be pretty tough to pull it away. That's a high ionization energy. But as you go down, here's that atom again, okay? Now we've got this big old atom down here. Man, that electron's all the way out here. It's so far away, so much shielding. It's barely being held onto. You can easily yank that away. That is a low ionization energy. The periodic trend is similar. When we look at the periodic trend for ionization energy, we're talking about what's happening from left to right. So again, we talked about the fact that the nucleus is getting stronger as I go across. So if my nucleus is getting stronger, it's the difference between this skinny little dude holding the bag of Doritos and this massive muscle. Wait, let's see if I can write muscles. Look at my muscles. Okay, those are quads, and then there's little calf muscles, and then there's the dude's forearms. Look at the size of his forearms. Okay, it's going to be a lot easier to get that bag of Dorito compared to that one. So, looking at the periodic trend, if I've got this big old atom out here, okay, that big old atom has got that thing way out here. I can grab that. Whereas this little atom over here, it's going to be a lot harder because it's a stronger nucleus. Now, there are exceptions to this at full orbitals and half full orbitals, and that's because you get a little stability from them. There's a great graphic representation of ionization energy in your PowerPoint, and you can really see, first of all, the pattern as you go across the rows, and second of all, you can see how messed up the D block really is. Last trend is electronegativity. And this goes hand in hand with ionization energy. Ionization energy is how hard do you have to work to get this bag of Doritos away from me. Electronegativity is how tight am I holding on to it. Okay? It's that tendency to hold on to electrons, to attract electrons to yourself. So they're really two sides of the same coin. Electronegativity is how tight am I holding. Ionization energy is how hard do you have to work. So needless to say, the two go hand in hand. If I'm holding on to my Doritos for dear life, you're going to have to work to get them. But if I'm holding on to them with 2 fingers, you can easily grab them. So when we look at the trends, we see it's the same as ionization energy. If I look at the group moving down, I've got more shielding. I've got less attraction for electrons. Okay, so up at the top, I've got this little bitty atom. Okay, down at the bottom, I got this big mamma jamma. Okay, so this electron versus this electron. This is a high electronegativity because it's going to be held on really tight. This is a low electronegativity. Looking at my periodic trend, okay, again, it's the same as ionization energy. As I go across, my nucleus gets stronger. So if my nucleus is getting stronger, we're back to that muscle man again, we're going to see a greater electronegativity. So with all this information, one of the things you have to be able to do is pick any 2 elements on the periodic table, and you need to tell me which one is bigger and which one is smaller. You have to be able to tell me which one has a high electronegativity compared to the other one. So I came up with a little trick to help you remember it. When you get a periodic table, draw a small circle up here with an arrow going down and a big circle. And then an arrow going this way and a big circle. Now, no matter what I ask you, you just look at your picture. Let's say I want to know which one is bigger, chlorine or iodine. Well, I look over here at my little cheat sheet. Iodine's lower, he's bigger. Let's say I want to compare chlorine and phosphorus. Well, there's, the small ones, there's the big ones, so phosphorus is bigger than chlorine. Occasionally your SOL will do things like which one is bigger, antimony or chlorine. Okay, so they're at a diagonal, but if I look at the way the trend goes, I can tell chlorine is definitely smaller. What neither your SOL or I will do is ask you to compare phosphorus and iodine. Okay, you're not going to have to do that kind of diagonal. Just the straight lines or ones that are fairly simple. Got rid of that red line for you. The other thing you can do to remember the other 2 trends is in this little circle, write high. In this big circle, write low. In this big circle, write low. Now I have all three trends together. My little atoms have high ionization energy, high electronegativity. My big atoms, both of them are low. So if I say again, okay, which one has the highest ionization energy, chlorine or iodine? You go back to your little cheat sheet over here. What do you know? It's got to be chlorine. Okay, which one has a lower ionization energy, cesium or fluorine? Well, based on that trend, it's definitely cesium. So these are the trends that you've got to know. There, of course, are others out there, but this is all we've got for this unit.